The modern web architecture, built on stacks like React and Node, is highly optimized for a very specific task: creating, reading, updating, and deleting data. But that efficiency hits a hard wall when you ask those same stacks to process intense mathematical computations natively. Try to force heavy algorithms through a standard data pipeline, and the system throttles. Memory limits are exceeded, the event loop blocks, and the entire application grinds to a halt. You see this breakdown immediately when developers try to natively run state vector quantum simulations, orchestrate autonomous multi-agent reasoning, or generate lattice-based cryptography in the browser. Yet, enterprise demand is pushing exactly these technologies, AI swarms and post-quantum security, into everyday commercial applications. You can't simply install a new software library to get around this. Integrating deep tech primitives requires a specific architectural blueprint designed to handle the load. We can examine exactly how this is done by looking at QMOOSA, a platform built specifically as a deep tech web stack. It successfully runs specialized AI agent swarms, real-time quantum circuit simulation, and NIST-grade post-quantum cryptography in a single unified interface. The surprising part is the underlying framework. It achieves all of this using standard tools: React 19, a Node backend, and a serverless Netlify environment. This diagram shows the difference. On the left is a traditional request and response cycle. On the right is QMOOSA, taking standard web requests and routing them to specialized compute nodes for AI, quantum mechanics, and cryptography. To understand how it routes and computes this data without crashing, we are going to reverse engineer its system architecture diagram from a blank canvas. By mapping this out, we'll see exactly how mathematically intense engines operate securely behind standard continuous deployment workflows. We start by defining the top level of the stack, the client layer. This visualizes the boundary of the React application, which is built with TypeScript and Vite. Its only architectural responsibility is managing user interface state and high-performance data visualization. It is completely isolated from the heavy backend math. Inside this layer, we find the distinct UI modules: an interactive AI workspace, a post-quantum cryptography lab, and a blockchain verifier. The quantum components require significant rendering capability, specifically the ability to draw state vector amplitudes and D3 probability distributions in real time, based on incoming data. So we add the quantum circuit designer and the 3D block sphere analyzer directly into this client layer. By strictly offloading the actual simulation algorithms to the backend, this layer acts only as a presentation matrix, completely sidestepping browser memory bottlenecks. With the front end established, we move down to the server side of the blueprint. Below the client sits the backend and serverless layer, anchored by a unified API router that catches every request from the UI. This router is the sole traffic controller for the entire platform. The front end never knows how the complex math is executed. It only knows to ping this router. If a user submits a prompt, the UI sends an API chat payload down to the router, which triggers the AI orchestration logic. The router forwards that payload to a dedicated Gemini service node, which interfaces directly with the external Google Gemini API. Instead of a single generic model, this backend logic operates a multi-agent swarm. It evaluates the prompt and delegates it to a specialized sub-agent, like a code agent, a quantum physicist agent, or a crypto agent. Keeping this centralized service design means the immense complexity of managing large language model context windows is completely abstracted away from the front-end repository. Next, the architecture must account for its most computationally heavy requirement: simulating quantum circuits. To handle this, the system uses a bifurcated design. It splits quantum requests into two distinct paths: local math simulation and external cloud hardware execution. The router splits the traffic, sending payloads either to a local quantum engine block or out to an IBM Quantum bridge. On the local path, the router catches a simulation payload and executes the intense matrix multiplication for logic gates, like CNOT and Hadamard, directly within the node runtime. The raw JSON array of gates and qubits is processed locally to instantly return state vector amplitudes back to the UI. Alternatively, the cloud path compiles that exact same circuit design into OpenQASM 3.0 code, dispatching it via REST API to external hardware. That OpenQASM payload is sent across the cloud, executing on physical IBM Quantum processors sitting inside dilution refrigerators. This bifurcation means developers iterate locally on complex algorithms with zero latency, and then seamlessly deploy those same algorithms to actual quantum hardware. The final requirement of the backend is facilitating enterprise security migration to withstand future quantum computing attacks. This requires strict compliance with the post-quantum cryptographic standards finalized by the National Institute of Standards and Technology. To implement this, the architecture includes a dedicated post-quantum cryptography engine. Its specific job is to generate ML-Chem 768 shared secrets and MLDSA digital signatures to comply with FIPS standards. We draw the PQC engine alongside a companion node, the audit engine. Both are wired directly back into the central router. The audit engine takes those newly standardized cryptographic tests and applies them to blockchain infrastructure. It performs automated static analysis on Solana Anchor bytecode and inspects EVM smart contracts to ensure they are utilizing post-quantum signature schemes. Integrating these NIST-grade logic checks as deployable endpoints turns quantum threat mitigation from a theoretical math exercise into a standard, automated, continuous integration pipeline. With all the components mapped out, we can review the architecture as a complete system. This diagram shows the exact boundaries between the client, the serverless backend, and the external compute nodes. If a user asks the AI to verify a quantum-safe smart contract, we trace the execution path. The prompt leaves the UI workspace, hits the API router, queries the Gemini service, triggers the blockchain audit engine, checks PQC lattice algorithms, and returns a consolidated verification. Because of the strict separation of concerns, the intense math required for lattice generation in the crypto engine never blocks the standard node event loop running the API router. The system functions efficiently because the computational weight is strictly isolated behind rigid architectural boundaries. Zooming out from the diagrams, this architecture represents a broader shift for software engineering. Working with frontier technology like quantum mechanics or post-quantum encryption no longer requires an isolated team of specialists building bespoke hardware infrastructure. The tools to deploy these systems are becoming highly accessible. Computations that were purely theoretical just a few years ago can now be executed directly within a standard Netlify serverless deployment. The future of web development is evolving past basic data retrieval. It relies on seamlessly orchestrating these deep tech computational layers as native components of the everyday web stack.